Hello, welcome. This is Jepsen 16. I know we said 15, but we're not about consistency anymore. We're about fun. I can't believe it's not acid. My name is Kyle Kingsbury. You might know me as Afer online. Pronouns are he, him, and my wonderful gift from the powers that be is that every database, bureaucracy, system I interact with breaks in horrible, mysterious ways, and the only thing I've been able to do about this is to write up my sadness. In order to find even more sad events, I've built a library called Jepsen. This is a distributed systems testing framework. You can use it to write tests of any kind of concurrent database, queue, cache, all kinds of systems. Jepsen combines four main ideas. First, it is an opaque box testing system. And by that I mean we don't inject any kind of probes, we do no simulation, we're not working on an abstract model of the system, we're running real binaries on real Linux machines the way that God intended. And as a result, we can't explore the state space as thoroughly as a simulation system can. We can't make proofs the way that an abstract system could, but we do find weird interactions between I/O and libraries and client anomalies, and that's really helpful. Also means we can test literally anything. Second, we do fault injection. Real distributed systems are characterized by recurrent partial failure, and so we inject those failures everywhere we possibly can and see what the system does. Third, distributed systems are fundamentally concurrent systems. They do more than one thing at once. And if your testing toolkit only does one thing at a time, it's missing out on all that fun. So for maximum fun, we do lots of operations at once on lots of nodes, and we have to design our system to account for that concurrent structure. In order to make that possible, we apply techniques from generative testing, like QuickCheck in Haskell or Erlang. We apply randomized inputs to the system, driving into some strange corner of the state space, and then we apply some predicate and ask, did the path we took to get here make sense? Does it obey some laws? Architecturally speaking, there are three main components in a Jepsen test. There is the operator, a lovely human being. There is the control node, usually your laptop or some EC2 VM. And there's a series of DB nodes which actually run the database or whatever you're testing. The operator on the control node will run a Jepsen test. That's just a JVM program, usually written in the Clojure language. And that thing makes SSH connections to all the DB nodes. On those nodes, it sets up instances of the system under test and connects them, so we have a fresh copy of the database to start with. We then run a bunch of clients, and the clients issue requests to all those machines. The machines communicate over an IP network, and together they should provide the illusion of a coherent system that doesn't lose any of your data. While this is going on, we make it difficult by using those same SSH connections and other means to, say, cause partitions. We can run IP tables commands to isolate machines from one another. We can create process pauses with kill with sig stop or sig continue. We can do crashes. We can do clock skew. Inside of Jepsen are a few major parts, and I want to touch on this because we've talked about effect systems so much here, and this is an effect system. You have a pure functional data structure that says, what I'd like to do next is read the value of X, and maybe after that we'll kill DB1, and maybe after that we'll set the value of Y to 2. It's some abstract representation of what you'd like the test to do, and it can continually unfold over time, changing in response to different inputs from the test. So we take the top thing off of that generator, and we add it to the history, which is an append-only log of everything we want to do. We'll call this an invocation operation. And we'll take that invocation, like read X, and we'll give it to a client, whose job it is to adapt the abstract read X and turn it into some horrifying thing like select star from foo, where ID is X. Black magic occurs, and what comes back is a completion operation. We say, I read the value of X, and it's currently 3, and I'm going to put that in the log. And then I can correlate my invocation to completion to tell me exactly what the span of time was when this happened. Completions can happen in one of three ways in Jepsen. They can complete OK, and we know they took place. They can complete with a failure, and we know they did not take place. Or something else could happen, like a timeout. And in this case, we actually log an informational message, but the invocation stays open for all time because that operation might take place next Tuesday. You don't know. This is just intrinsic to the way that distributed systems work. So this is going on concurrently. All of the clients and the nemesis, which introduces faults, are pulling operations off the generator, applying them to the system, getting completions, putting them in the history. And this means our history is a concurrent log of all the abstract things the system did over time. And with that log, we could start to ask questions using a checker, like, Does this history look like repeatable read to you? For instance, if the checker can find a write of the key x equals 5, and that's the only write of 5, and it fails, and some other transaction in the system reads x equals 5 and commits, we know that we have an instance of G1A, aborted read. A failed transaction was visible to some reader. That invalidates read committed. Hooray, we found a bug. That's my life. So I want to talk to you about 3 databases in this talk, 3 case studies, and then we'll talk a little bit about where I'd like the industry and academia and vendors to go together. And to start off, I want to introduce this wonderful database called RavenDB at version 6.0.2. RavenDB is a distributed document store intended for online transactional processing workloads. It offers, quote, ACID database transactions across multiple documents and across your entire cluster. It was the pioneer database to offer ACID in a non-relational context. Please do not fact check this. And has any combination of database operations that can be combined in an ACID transaction. How do you do transactions? Well, the documentation says to use a session, which represents a single business transaction. Great. What are the semantics of these sessions? Well, all actions performed in documents are fully ACID. In a single transaction, all operations operate under snapshot isolation. Hang on a second. Snapshot isolation is not ACID. It's not fully isolated, right? It allows write skew. So there's some sign of discrepancy in the documentation. And the CEO clarifies that RavenDB offers snapshot isolation by default, and transactions are effectively going to observe serializable between operations on the same node. Okay, those are still both fairly strong properties. We should be able to measure and tell which is which. By default, SI, possibly serializable in single node. The documentation also says that there's 2 separate transaction paths, a single node path, which is the default, that uses AP eventually consistent semantics with last write wins conflict resolution, and a cluster-wide transaction path, which offers stronger consistency by using the Raft consensus algorithm. And that one I very much would expect to get me to serializable, because Raft offers linearizable or sequentially consistent semantics itself. RavenDB goes on to say, concurrent cluster-wide transactions are guaranteed to appear as if they are run one at a time, serializable isolation level. Great, that is a strong testable claim we can put into a computer. And in 2020, RavenDB did just that. They wrote their own Jepsen test, where they compared MongoDB's snapshot isolated transactions to RavenDB sessions, and in a webinar, they claimed that, quote, everything works. I love this phrase. I wanted to see it for myself. So I wrote a test which randomly generates transactions over lists of integers, and those transactions have 2 types of operations. You can either read the value of some list, like show me list X. Okay, it's 1, 2, 3. Or I can append a unique integer to some list, like add 7 to list Y. Make up random transactions, span them into the system, and through magical means I don't have time to explain, this will tell us a lot about transaction safety. We do this basically following the webinar and the documentation's guides for transactions. We open a single session for every transaction. If we want to read something, we call session.load. If we want to append something, we use session.load to read the current value. We mutate it in place, and we call session.store to save it back. All of those mutations are buffered in the session until we call session.saveChanges, at which point the transaction commits, data is flushed back to RavenDB. Seems straightforward enough. In single node RavenDB clusters, this is systems distributed, right? With transaction mode single node, which is the default, and optimistic concurrency false, you get transactions like this pair. Transaction 1 reads X and sees the list 1, 2. It appends 3 to X. Transaction 2 reads X and sees the list 1, 2, and appends 4 to X. Huh. This is the definition of a lost update from the snapshot isolation paper Berenson et al. 1995. Both of them read the same data, they both mutated it, and they both successfully committed. First committer wins in a snapshot isolation is supposed to say, hang on, one of these transactions must abort. Otherwise, one of their effects could be lost. What actually happens is both of them win temporarily, and they fight. You get X equals 1, 2, 3, and you get X equals 1, 2, 4, and then they're resolved via last write wins, and the write of 3 is sort of forgotten for the rest of time. What wins is 1, 2, 4, 5, and so on. So that's forbidden under snapshot isolation, and it happens constantly in healthy single-node RavenDB clusters. Almost half of all keys in our test lost updates under the defaults. OK, so what about a single-node cluster where we run transaction mode single node and optimistic concurrency equals true? What's this flag for? Well, it prevents lost update. But it allows transactions like this, where transaction 1 appends 1 to x and 2 to y, and transaction 2 reads x and observes nothing, and reads y and sees the list 2. There is a read-write dependency here. Transaction 2 must have happened first because it did not see the append to x. But there's a write-read dependency. Transaction 1 wrote 2, and that was visible to transaction 2. So it's kind of like transaction 2 saw some, but not all of T1's effects. That's called a fractured read. Big surprise, this is also prohibited under snapshot isolation, as well as a bunch of weaker levels, like read atomic, causal, prefix, parallel snapshot isolation. In short, it's not something you want from a ACID database. But this isn't so bad, right? Because the docs did hint that there were 2 transaction paths, and this is the weaker one. What does the stronger one do? The one that offers supposedly serializable semantics by using transaction mode equals cluster wide. Well, it actually still allows fractured read. It does the exact same thing. And I was looking at this, tearing my hair out, and I eventually gave up and filed some GitHub issues, and the CEO explained that, well, RavenDB doesn't attempt to provide transactional semantics over the entire session. Rather, it provides transactions over individual requests. and clarifies we don't support a transaction over more than a single HTTP request. And I was looking at the documentation. It's like serializable isolation over any combination of database operations, but not if you do more than one request. Like what is the session for? What is a single business transaction if not a transaction? Like this is the only mention in your docs. So as far as I can tell, RavenDB doesn't have interactive transactions at all. And it just shouldn't be thought of in that way. It's not like the databases it compares itself to. The new documentation reflects this. They're not going to fix the behavior, but they now say that the term ACID transaction or transaction refers to these storage engine transactions. That is to say, the way a single node lays out data on its hard drive. So that's a goalpost. And they also say that there's no support for transactions with multiple requests, and that sessions are not, in fact, transactions, which is an improvement, and I'm hoping it will guide people to use the system more safely. OK. MySQL. Version 8.0.34. MySQL is a workhorse relational database. It needs almost no introduction. There are multiple replication architectures, all of which we'll ignore for purposes of this talk at systems distributed. It offers 4 isolation levels, ranging from read uncommitted to serializable, but I'm really interested in the level called repeatable read. And repeatable read, in a nutshell, says if I read something in a transaction, no one else is allowed to change it until I commit. That way my reads of it are repeatable. Or if I read something and then I write to it, I'm guaranteed nobody else messed with it. And the documentation for MySQL actually says explicitly, all consistent reads, and that means the default kind of read, like a select, all consistent reads within the same transaction read the snapshot established by the first such read in that transaction. OK, let's try it. So I read a test, originally for replicated MySQL, and it does very odd things. And so I back off to single node MySQL. And I do these list append transactions where I encode a list as a comma-separated text field in a single row. I access them by primary key. And if I want to add to them, I'll just use SQL concat. This is like the simplest possible schema. And those transactions do things like this. T1 reads x nil and appends 1 to x. It reads its own write and sees the value of x is just the list 1, which means it executed first. T2 reads x nil and appends 2 to x. Both of these transactions committed. This is the exact same problem. It's lost update, right? Both transactions saw the same state. They both changed it. They both committed without seeing each other's effects. They could lose something here. And this is just how MySQL works. It's illegal under snapshot isolation, and essentially every formalization I know of repeatable read. It may or may not be illegal under the ANSI SQL repeatable read level, because the standard is hot garbage. For more on that, see AJA 1999. Seriously, we've known this for 30 years, and the standard is still awful. And I don't understand how our industry is like this. Okay, I'm getting sidetracked. This is old news. I mean, 'tis known, Khaleesi. Martin Kleppmann in 2015 or so put out this wonderful thing called Hermitage, where he demonstrates a bunch of ways that different SQL databases don't do what they claim. And we know that lost update is one of those things that repeatable read does. What I didn't know until recently is that non-repeatable reads are also possible at repeatable read. So this is a single repeatable read transaction in MySQL. We select a person's name, and we get back Pebble. And then we update their gender to femme, and we select their name again, and the name suddenly becomes Moss. I didn't write that. Where did it come from? This is like the definition of P2, non-repeatable read. Some other transaction, when I updated the gender, that other transaction was allowed to clobber this field in the same row. So, like, we violated internal consistency. It looks like other people are stepping on top of our toes. We're trying to do a transaction. Well, okay, Kleppmann suggests that maybe repeatable read is monotonic atomic view, something that's much weaker. And MAV requires that once you see some of a transaction's effects, you see all of its effects. That sounds straightforward. So let's have a table with two rows, X and Y, and we'll have a value column and a no-op column, something we can update to mess with the invalidation stuff. And I'm going to run a bunch of write transactions, which are all exactly the same. Every one of the write transactions increments X's value and then increments Y's value, in that order. And so we should expect to see the committed values of X and Y go from 0, 0 to 1, 1 to 2, 2, and so on. Here's a transaction that runs concurrently with those writes. We read the value of X and get 0. We update the no-op of row Y and read Y's value as 1. And then we read X's value, and it's still 0. This is even more bizarre, right? Like, we've observed an increment transaction, and then we unobserved the transaction. It's like we got to see, we got to see it for a minute, and then it was gone. This violates monotonic atomic view, because once we saw some of T1's effects, we should have seen all of its effects. So it must be weaker than that. Something between read committed and MAV. This gets even weirder when you think about the snapshot language that's all through the InnoDB docs. Because if you think about the order of increments here, we always increment X then Y. So the committed states of X and Y had to go 0, 0, 1, 0, 1, 1. But there's no time when the transaction could have read a snapshot that had 0 and 1 together. That never existed in the database. So how is this even remotely a snapshot? What's paradoxical to me is that I wrote this up, and then everybody in the MySQL mailing list saw no problem with it. Sorry, MariaDB's mailing list. And eventually, we went back and forth and managed to convince some people that it was a problem, and they're working on it. But the bottom line of all of this is that if you're a MySQL user or a MariaDB user, they both exhibit the same behavior at the default repeatable read level. Namely, it allows lost update, which means that any ORM style, like read some data, modify it in memory, write it back, that's unsafe unless you use explicit locking techniques like select for update. Reads are not repeatable. Reads are not even monotonic. And claims about snapshot isolation are completely wrong. So, cool. The lovely folks at MariaDB have been really helpful about this. We've gone back and forth, and they're doing some Jepsen testing of their own. They've added this flag called InnoDB strict isolation, and that appears to prevent the non-repeatable and non-monotonic reads. So hopefully that will be coming soon to a InnoDB near you. Woo! All right, third database, Datomic Pro 1.0.7075. Datomic is a weird and wacky and wonderful database. It's a serializable online transactional system intended for storage of record. And it's also a temporal database, which means it has an explicit model of time. You actually know when facts were asserted about this system. It's immutable, mostly. You can excise records, for example, if you have legal constraints or accidentally leak, say, a PII into the DB. And you can compact old history if you want to. But otherwise, you get access to all past states. It's built on top of a pluggable storage layer, so it delegates its storage to other systems and provides transactional semantics on top of it. And it offers data log, graph traversal, and ODM-style query APIs. Architecturally, Datomic is built out of three main parts. The peers run the application, and they include what's called a peer library, which is like a really fat client. And that thing's job is to satisfy queries by pulling down data from storage. Transactors, of which there's typically only one active at a time, are the only thing that do mutations in the system. They execute transactions and push data up to storage. And storage stores two types of data: immutable data in very, very big immutable trees. These are functional persistent data structures, a lot like hash-mapped array tries. And then they also store a handful of pointers to the roots of those trees. And those things have to have sequential consistency so that they can be updated safely. So my peers execute reads against storage. They pull in chunks of those immutable trees as necessary to satisfy queries. They cache them aggressively. If a peer wants to write something, it sends it over to a transactor, which does any reads required, computes new values for trees, and writes them to storage, and finally computes the new roots and writes those pointers to storage, at which point the transaction commits. Logically, Datomic looks like a big spreadsheet with 4 columns: entity, attribute, value, and time. If you've ever seen RDF triples, this is going to look really familiar. We're just adding a temporal dimension. So this database has a single entity, number 1, whose name is NK Jepsen as of time 1, and whose Hugo count was 2 as of time 2. But this is not the only state available. I could look back in time at a previous value of the database, and maybe at time 1, her Hugo count was only 1. And in fact, in Datomic, I can reach back as far as I want, modulo compaction, and see ancient versions of the database. Every transaction produces a snapshot of the database which is accessible to everyone for all time. That means that I can do like long-running analytics queries without blocking anybody else. I can get a snapshot and pass it off to some other node, and I'm guaranteed we see the same state. Really cool stuff. The query API looks a little weird too, and this isn't necessarily safety related, but it's such a neat idea. In most databases, you issue a query and you just get whatever the database is at now. In Datomic, you explicitly say, get me a version of the database. Let DB be whatever the database is right now in this connection. And then I can use this queue function to run a query on that snapshot of the database, and it will pull in chunks from storage as necessary to satisfy the query. And any number of queries I run on this immutable snapshot all execute at the same logical time. So I get transactional semantics for read-only operations. If I want to do a whole bunch of different queries, I'm guaranteed they all have the same semantic timestamp. And I can pass this thing off between nodes too, because it's just identified by a number. A write is executed by sending a data structure to the transactor called a transaction request. And this thing is written as a vector of vectors, where the first element in each vector gives you the type of operation you're asking for. There are 2 fundamental operations, add and retract. Here I'm saying I want to add the fact that entity 4's name is Beyonce, and I want to add the fact that entity 4's alter ego is Sasha Fierce. Now this transaction would execute, and it would merge those tuples into the state of the database. But I can also use what are called transaction functions. I could say, I want to drop an album by artist 4 named Renaissance. And that thing will look up a function called drop album and call it with the current state of the database and the artist and the album. And it will produce a new transaction request structure, which is recursively expanded until only adds and retracts remain. And that's what gets incorporated into the DB state. So these are like store procedures, right? I can do arbitrary functional transformations of state. And the point of these things, per the docs, was to atomically analyze and transform values, quote, to ensure atomic read, modify, update processing and integrity constraints. Neat. So let's ensure an integrity constraint by doing some atomic processing. I want to model a state machine with 3 possible states. The initial state I'll represent as nothing. And then I'll say that a grant is approved by creating an approved at tuple. And I could also deny a fresh grant, which will create a denied at tuple. So I could do exactly one of these transitions. I can approve a fresh grant, or I can deny a fresh grant. I can't do any other transitions. I can't approve, I can't approve, deny. Only one transition allowed. That's the invariant I want to enforce. And to do that, I'll write an approve function, which takes the current state of the database and some grant ID. And then I will query it. I'll say when it's approved or denied, if I have the approved at tuple or the denied at tuple for this particular ID in this version of the database, then I'll throw an exception. Say, hey, this is an illegal state transition. The transaction aborts. No data is written. If I don't throw, I'll say, oh, great, I want to add the fact that this particular grant ID was approved at the current date. Deny looks identical. It just adds a denied at field. And if you think about it, by checking to make sure that no approved at or denied at tuple exists before we create it, we should ensure that single transition property. You can only approve or deny, not both. So to test it out, we'll have some clients that run concurrently. One of them will run a transaction that tries to approve grant 123. The other one runs a transaction that tries to deny grant 123. And then we can say, do we ever find a grant that's both approved and denied? And the answer is no. Wonderfully enough, in every test I've run, Datomic looks to be strong session serializable. That is to say, its transactional history is equivalent to one in which the transaction is executed in total order, and also that order is consistent with the order every single node executed their transactions, both reads and writes. Even stronger than serializable. And in fact, if you restrict yourself to writes only, it's strict serializable. It obeys a global real-time order. So this is one of the strongest things I've ever seen. However, let's imagine a client issues a single transaction which asks to both approve grant 123 and to deny grant 123. Show of hands, who thinks this transaction commits? Who thinks this transaction aborts? About 50-50, okay. Well, it does in fact commit. It produces a state in which the grant is both approved and denied. Why is that? Well, initially, the transactor starts off with a fresh database state. Let's say it's the empty set of tuples. And it then calls the approve function with that empty state and grant ID 123. The approve function says, is there an approved at or denied at tuple in here? I don't see one, so I'm going to add 123 was approved at the current date. Then the transaction calls the deny function and passes it DB0. Again, immutable snapshot of the database. And it says, is there an approved at or denied at for 123? No? Great. Add the denied at tuple. Then it takes the set union of those tuples and produces the output state in which the grant is both approved and denied. Somehow we took two transaction functions which were safe when run in separate transactions, and by putting them in the same transaction, they became unsafe. That's really unusual. There's very few systems that do this. And you might be staring at the docs going, hang on a second, what about this atomic read, modify, update processing? The docs say that transaction functions are serialized by design, and the functions are called, quote, in turn. And that might lead you to conclude that they execute in series. But the docs are also very clear. Transaction functions are past the value of the DB currently as of the beginning of the transaction. And so these semantics are exactly what you get. Like, this is what the docs say happens. And I was tearing my hair out for no good reason. In most systems that are serializable, and I'm making up these terms externally and internally for lack of a better name, not only does the system look equivalent to executing one transaction after the next, but also inside a transaction, it executes the steps in order. That is not how Datomic works. Datomic is externally serializable, but inside each transaction, everything executes all at once, or appears to. So that's really unusual. Is this serializable? Well, trivially, yes, because when we talk about serializability, the informal property we're talking about is equivalence to a total order of execution. That's very obviously true. It's the intra-transaction semantics that are messed up, or correct, depending on how you look at it. On the other hand, absolutely not. Almost every formalization and existing database I know of uses serial intra-transaction semantics. As early as 1979, Kung and Papadimitriou say a transaction is a finite sequence of transaction steps, thus our transactions are straight-line programs. Ajo, Liskov, and O'Neill's germinal work in 2000 on weak isolation levels say that if a transaction modifies X and later reads it, it will observe its last update to X. Same thing in the abstract execution formalism from Gottsman et al. 2015. Within a transaction, the database provides sequential semantics, and again and again and again. So what is this? Right? Is it serializable? Is it not? I've chosen to call it externally serializable, but that's not a great word. Or maybe intra-transaction serializable. Maybe we need a new formalism. Maybe there should be new mathematics to describe these kinds of rules. And there are some advantages to doing this. For example, Datomic can guarantee you that every single visible thing in the database is the product of a committed transaction. And moreover, every one of them has an associated timestamp and specific transaction. You can look up what wrote that thing. That's not true in ordinary databases. If I go to Postgres and I do a read, I might see committed state, or I might see some hot garbage that the earlier statements wrote. Now, is it hot garbage? Well, what we're trusting is that transactions are written locally, and you can kind of look up and down in the transaction and tell what its effects should have been, and if it's safe to read that data or not. But maybe that's confusing. I don't know. Bottom line, Nubank, the makers of Datomic, think this behavior is unlikely to affect real users. As the possibly biggest user, they're a major bank and deploy Datomic in almost all of their operations, I think that's a powerful argument. They say that most of their transactions are very simple. They don't do many transaction functions. And even if they did have an accidental conflict, there's a conflict checker which aborts the transaction if you ever assert two different values for the same entity and attribute. That's a lot like the first committer wins principle. We've seen lost updates. In snapshot isolation, if you try and write two values to the same key in a transaction, one of them must abort. Datomic has kind of the same thing, but inside of a single transaction to control the concurrency, as it were, of the intra-transaction semantics. There's almost like a symmetry there between snapshot isolation and the internal dynamics of the transaction. Finally, there's a second mechanism you can use to constrain database states called an entity spec. This is a function which receives the entire state of the DB prior to commit and can interrogate it. So you can use that to ensure safety as well. Finally, Datomic has gone and rewritten their documentation. They've expanded a lot about the transaction architecture and much more besides. And so I'm hopeful that this possibly confusing part of the docs is now clear and everybody should be able to figure out how to use it correctly. To recap, doing really simple tests, sometimes even on single nodes, can yield really surprising results. And I want to encourage you to do 4 things. First, start by doing some end-to-end tests. As a part of this complete testing breakfast, in addition to your formal models and your proofs and your model checking and your unit testing and all that cool stuff, do some tests where you run the whole system end-to-end and ask, hey, do we lose any data? Do I ever allow you to double register the same username in my registration system? Run those tests with fault injection. These particular cases from the last 6 months of my research, no faults required, but generally in Jepsen's history, most of the bugs I find come about because of network partitions or crashes. So try introducing those. IP tables, TC, kill, you can get a lot of mileage out of simple tooling. Try techniques from generative or property-based testing. What I found consistently is that example-based tests, like the ones that Postgres has for testing transaction safety, they write out a sequence of transaction steps by hand and verify that's correct. That's really good for regression testing. It's efficient. It's something you can reason about. But it also has blind spots because it's not generating weird transaction shapes. You can find unusual corners in the state space by spamming unusual transactions. When you do that, you may have to get more sophisticated safety checkers. You can get a lot of mileage out of simple things like, did I lose data? But if you want to do more advanced checks, one of the projects I've been working on is called L. This is a collaboration with Peter Alvaro. It analyzes those list append histories and can tell you a lot of things about system safety. All of the bugs that I've talked about here were found with L. When we talk about safety, there are 3 separate concepts that sort of overlap. One of them is the abstract formalism of the system, the mathematical model about how transactions relate in a graph structure or something like that. But when you look at the way that documentation describes system behavior, it's rarely doing it in a formal way. It says something like ACID or maybe snapshot isolation. Maybe it says reading from a snapshot. And the semantics that aren't formally defined, there's a lot of wiggle room. And the documentation may bear no relationship to the intuition that users have in their head. And that's what ultimately governs the transactions people write. So I'd like to align these three things. I want to get people writing documentation with a little more formal language. I want to get documentation closer to people's intuition, my own included. Sometimes I come to a system like Datomic, and my own history with databases leads me to believe the wrong thing about the way it should work, when the documentation was quite clear. Ultimately, these should ground out in meaningful invariant violations, like people losing access to their medical records, or people accidentally getting each other's money. We want to prevent that stuff. For users, I want to recommend spending some time in the formal literature. In particular, if you're doing any kind of transactions in SQL, take a look at Atul Ajja's paper with Barbara Liskov from 2000 on weak isolation levels. It's a fantastic primer, and it will help you understand why the standard is so bad. Second, read the documentation for your system carefully, because documentation is often contradictory. Third, documentation is wrong, so you should probably be checking your application to see if it's safe on top of the system you're actually running. And if you find a discrepancy, write it up. I would love to see more blog posts about people saying, oh my gosh, I thought the system did X and it really did Y. That's really useful fodder for testers and for vendors. For vendors, I want to see people reading more of the literature and making up less of their own safety semantics. Enough said. I would love to see formalized safety models for databases. And it doesn't have to be the most formal thing in the world, but have some sort of reference point like, oh yeah, we're aiming for Ajja's semantics around repeatable read, or we're looking for generalized snapshot isolation. If you have some sort of touchstone literature, it's a lot easier to map back and forth between those intuitions and the formalism. And then communicate that through your documentation with clear examples. Finally, use those formalisms to write tests that actually measure those properties in the system you're building. Academics have a problem, and I guess I'm sort of an academic, so I should point this at myself. We keep, the formalisms that we have don't necessarily map well to new systems. Datomic's semantics are not that of a standard SQL database, and maybe they shouldn't be held to the same standard. Things like Kafka, for example, they have transactions, but if you try to figure out what those semantics look like for things like read committed or serializable, it's not necessarily clear how to map them back and forth in the existing formalisms. So maybe we should have new ones driven by research in the field. And finally, we have a connection problem, because the papers that are defining these abstract models are not being read by users and vendors. And with good reason. I can stare at these papers until blood forms on my forehead and only understand a quarter of them. They're impenetrably dense mathematics with a few exceptions. And I want to point in particular to the success of the Raft paper. Angro and Asterhout were rejected several times, essentially because we have Paxos at home. We already have a consensus paper, like why write more? But the Raft paper did something really special. It was written to be understandable. It addressed production concerns like membership changes, and it had a one-page explanation with pseudocode and variables. And having that kind of pedagogically focused paper, I think, spurred an entire renaissance in the industry. So many databases stopped inventing their own consensus systems and started building things based on Raft, and safety has gotten better as a result. So maybe we should do more of that. I owe so many people thank you for this work. Nubank funded the research on Datomic. MySQL and RavenDB performed independently without compensation. My collaborator and co-author, Peter Alvaro, was invaluable. We worked together on the MySQL project, as well as much of the L checker. I also want to give a shout out to the University of Portugal's Inesc, which has been building fault injection tooling I don't have time to talk about in this talk. In addition, a whole slew of friends and colleagues and open source contributors made this work possible, and I want to say thank you to all of them. Thank you as well to all of you for your time today. If you want to read more about this research, it's all free to run and see for yourself on Jepsen.io. Thank you.